Hey everyone, let's dive right into this explainer and see how we can take a simple, everyday school kitchen garden and completely transform it into a highly integrated scientific experiment. We're looking at a blueprint today that perfectly merges that dirt under the fingernails organic wisdom with cutting-edge artificial intelligence. It is absolutely a fascinating look at how we can teach modern agriculture right in a schoolyard. You know, there's a brilliant philosophy from our source material that really sets the tone for us today. An undocumented garden is just a hobby. A documented garden is a scientific experiment. We aren't out here just tossing seeds in the dirt and hoping for the best, right? We're operating as citizen scientists, documenting a living ledger. Literally every drop of water, every little sprout, and every single data point matters. So here's our mission briefing for this whole dirt-to-data journey. We're going to quickly cover preparation and safety, then move into crafting the biological engine, precision architecture, nurture and defenses, AI integration, and we'll wrap it all up with the smart harvest. All right, let's kick things off with part 1, preparation and safety protocols, where we lay the groundwork. Just to give you a quick roadmap of how we actually get from a totally empty patch of dirt to a thriving ecosystem, this blueprint follows a strict 5-step life cycle. As we move through these, you're going to see how we progressively layer on biological complexity, and then top the whole thing off with technological sophistication. Now, what's really interesting, maybe even a bit surprising, about this approach is something called the dual shield safety protocol. Because, this garden relies so heavily on data and apps, it actually treats cyberspace with the exact same level of caution as the physical garden itself. Think about it like this. On the physical side, bending at the knees to lift heavy pots so you don't wreck your spine, or wearing gloves to dodge soil-borne infections, that's all critical. But then look at the digital side. It is equally important to make sure we're never sharing personal location data, to only use these AI tools under adult supervision, and to carefully vet any photos before they get posted online. It's just an incredibly comprehensive approach to keeping students safe on all fronts. Moving on to our first major physical task. Site selection, or what we'll call strategic geography, because, you can't just plant anywhere and expect magic. We actually have to map out the solar trajectory to guarantee maximum sunlight for photosynthesis. We also have to check the drainage gradients so water naturally runs off. Nobody wants root rot, right? And for that very first crop, the blueprint strongly advises prioritizing fast-growing, vitamin-dense leafy greens, think spinach, and herbs like coriander, just to get that ecosystem established rapidly. Okay, moving right along to section 2, crafting the biological engine. So, with our site locked in, we have to create the fuel for our ecosystem. Basically, we're engineering our own fertilizer here. We start with the chamber, which is usually just a bin with some drainage holes, and toss in some biodegradable bedding. Then comes the fun part, the fuel. This is where we introduce Eisenia fetida, otherwise known as red earthworms. These little guys act as biological catalysts, literally eating and converting biodegradable school meal waste into incredibly nutrient-dense plant food. But, and this is a huge but, you absolutely must keep meat, dairy, oily foods, and citrus out of the bin. Seriously, no citrus. Those things will harm the worms and just invite a bunch of unwanted pests to the party. Which brings us to section 3, precision architecture and planting. Now we get to transition from engineering the soil itself to actually structuring our planting zones. And the architectural difference between methods is actually quite striking. On one hand, you have very shallow, meticulously spaced furrows that are perfect for sprinkling seeds. But contrast that with the other approach, where you need deep, custom-sized holes, precisely dug to perfectly match the fragile root systems of transplanted seedlings. So the really crucial takeaway here is understanding the different ways we close these up, whether you're just lightly covering and gently patting down those sown seeds to get good seed-to-soil contact, or you're firmly packing soil around a transplanted stem so it perfectly matches its original container level, the data requirement doesn't change. All of these zones must be immediately marked with date-stamped labels. I mean, think about it. Without tracking the date, we literally can't measure our growth metrics. It's back to that whole science experiment philosophy. All right, let's jump to section 4, nurture and organic defenses. Okay, so once our seeds and seedlings are safely tucked into the ground, our focus completely shifts to sustaining all that growth. If we look at this framework from the bottom up, based on the hierarchy of what a plant actually needs, there's a really clear structure.
It starts right at the foundation with hydration. We're talking strict daily soil moisture checks. Then we move up a level to structural support, like gently tying those fragile little stems to bamboo poles with soft strings so the wind doesn't snap them. And finally, at the top of the hierarchy, we have perimeter security. This means erecting physical barricades like geometric fences to protect the beds from careless foot traffic or stray animals wandering through.
But hey, not all threats are big stray animals, right? Gardens are constantly under siege by tiny invaders, caterpillars, whiteflies, aphids. Now, because chemical pesticides are a total no-go, they just devastate the broader ecosystem and kill our helpful soil microbes, we deploy an organic botanical chemistry recipe instead. By using active neem oil and giving it a kick with some garlic and chili pepper, we can safely disrupt the feeding patterns of these pests. You just mix all that up with a mild soap binder, load it right into a spray bottle, and selectively apply it just to the foliage that's affected. It's smart and it's safe.
Next step is Section 5, AI and Data-Driven Cultivation.
Let's step into the really modern phase now and look at how all this builds into an integrated digital layer using artificial intelligence. Modern agriculture relies heavily on what this blueprint brilliantly calls the digital botanist. It's the ultimate bridge between dirt and data. By just using smartphone scanners right out there in the garden beds, students can monitor biodiversity, track plant health, and identify potential threats with absolute precision. I mean, think about how powerful this actually is. Utilizing optical character recognition, or OCR tools like Google Lens, guarantees that we don't accidentally yank up some perfectly harmless native plant just because we thought it was an invasive weed. And even better, we can literally scan insects to confirm if there are beneficial pollinators, like, say, a helpful ladybug, before we even think about applying our organic neem spray. It just completely takes the guesswork out of the whole equation. And it goes way beyond just identification. These AI tools can actually cross-reference the specific needs of our plants with local weather forecasts to formulate highly precise watering schedules. So no more accidentally overwatering right before a week of rain. Plus, by assigning exact geographical coordinates to all the photos and videos, which is called geotagging, students are building a permanent digital map-based record. This means next year's class can see exactly what was planted, exactly where it was, and how well it thrived in the school's unique microclimate. And finally, we arrive at Section 6, Harvesting the Smart Ecosystem. We finally reach the absolute best part, the culmination of our living ledger. It's time to reap the rewards of our documented experiment. But believe it or not, harvesting requires just as much care as planting. If you harvest improperly, you can severely damage the plant and completely ruin future yields. That's why we practice what's known as precision harvesting. For leafy greens like spinach, you have to very carefully snip just the outer leaves down near the base, which allows the inner crown to keep on growing. And for herbs like coriander, you've got to harvest them before the plant flowers, or bolts, to make sure you're getting maximum flavor and vitamin density. Now, this systems map really brings the whole shebang together. You can clearly see how the natural inputs, the sun and the rain, combined with our homemade vermicompost, actively feed the plant. Then, on the other side of the loop, AI scanners and geotagging collect the data, and that data informs our human actions, like whether we need to adjust our watering or nourishment. It is just a perfect demonstration of how biology and technology continuously talk to each other to engineer a truly resilient, sustainable system. As we wrap up this explainer today, I really want to leave you with a thought. We have just walked through this highly structured, entirely data-driven blueprint, and we've proven that this incredible synergy between old-school organic farming and modern digital tracking works absolutely beautifully on a micro scale. But imagine what happens when we take this citizen science and scale it up. I mean, if a 6th grade class can optimize an entire harvest using just a smartphone and a box of earthworms, how might these exact same principles reshape the entire future of global agriculture to feed the world sustainably? Definitely something to think about.